Hello everyone, I am Dr. Sachidanand Sen and we are on the fifth lecture for the battery management system subject, and today we will try to cover the subjects on state of charge and state of health of the battery. These two are the most important parameters, and how to estimate these things, and what are the significance, applications, and what are the procedures involved. That part we are going to see today. So first we will deal with the state of charge and introduction to state of charge. So first of all, let us know what is state of charge. In short, it is represented as SoC, which is an analogous to a fuel gauge in a battery. It tells us how much energy remains. Like you might have seen in, suppose, bikes, you are having a fuel meter, or in cars also it is there. So 0 towards empty means the tank is empty, and when it is full, so you can say it is having the full capacity. Let it be petrol or diesel, anything. So in mid, so it is half filled. So like that. So it shows how much of remaining fuel is there in the vehicle. Same way, for a battery, we can say state of charge is nothing but remaining charge left in the battery, or you can say charge left in the battery divided by total capacity of the battery. So Q rated value of the battery multiplied by 100, because this is generally represented in percentage. So Q remaining is nothing but the charge left in the battery divided by full. So it gives the fraction of charge that is remaining. Similarly, for laptops or in mobile phone batteries also, we will be able to see 80% remaining, 20% remaining, like that. So that remaining percentage, and these things are not measurable. These are basically estimated using some algorithms, and that is the factor that we are going to learn. What are the steps involved in estimating the state of charge. So why the state of charge is important? It prevents overcharging and over discharging. So when as soon as it reaches 100%, we generally prefer to remove that one. Similarly, as soon as the battery goes below 20%, or in some case 15%, so some kind of alert or warning signals will come in laptop or in mobile phone. So that is undercharging. So we are going for connecting the plug charger. So like that. So it is crucial for battery management system in EVs and grid storage. Okay. So it helps in safety, improve the safety, battery lifespan, and energy availability prediction. So how much energy is remaining in the vehicle? If that much awareness we are having, so definitely it will help us to take better decisions. Okay, that how much distance we can yet cover before draining the battery completely, or whether we will be able to reach our destination safely or not. So these things are addressed properly if we are continuously able to monitor what is the remaining amount of charge in the battery. Now coming to the methods involved in estimating this one. So because this is not a directly measurable quantity, means there is no instrument available presently which will directly simply give you the remaining state of charge of the battery. So there are certain algorithms which we are using to estimate the magnitude or the remaining charge, and for that definitely some input is required for the algorithm, and those inputs are nothing but the measured quantities. Okay, something which we are able to measure, do the measurement using some instrumentation, basic instrumentation. So first method is called Coulomb's counting method. It is also called ampere hour integration. So it measures the current flowing into or out of the battery over time. So it helps us to know how much current is entering into the battery or how much current is drained out of the battery. Okay, so at any particular time interval t, okay, a state of charge will be nothing but initial state of charge at particular time instant, suppose at origin 0 time. Okay, t0 is nothing but the point from which we are trying to do our measurements. Okay, it is something we are knowing already. So initial state of charge minus 1 divided by total capacity of the uh, battery multiplied by multiplied by integration between t0 to t, time t0 to initial time to the final time, and of course current is the integrating factor here. Okay, with respect to time we are doing this integration, and here minus sign is represented as charging. If during charging this current I of t is taken as negative, so here automatically we will get a plus sign when we are considering the charging case, because charging means state of charge will increase with time, so definitely it has to be plus. So charging current is taken as negative, discharging taken as positive because current is coming out. Okay, so the state of charge will be gradually reducing with the passage of time as we are going for discharging condition. Okay, so this is the first and simplest method, and here some hardware based installations are required, like current sensing, because continuously we need to sense the magnitude of current. So for that purpose current measurement sensors are there, like Hall effect sensors or shunt sensors. Okay, then microcontroller for integration. Definitely without microcontroller continuous monitoring, data analysis is not possible. This is the advantages of this type of uh, technique is it is simple implementation, real time estimation is possible. And what are the disadvantages of this one? Accumulation of drift and offset errors. Okay, accumulation of drift and offset. Of drift means suppose it is deviating, suppose that this initial value of the charge is not known to us properly, what was the exact value. Definitely some assumptions need to be taken, or the initial guess need to be made, so that might be erroneous, so that can create some drift. Offset, drift is nothing but some deviation from the origin point. Okay, origin point or the actual value you can say. So definitely it needs accurate initial state of charge, so that initial value need to be somehow measured or estimated priorly. Some initial guess is required, so that is also a disadvantage. Then sensitive to sensor accuracy and noise. So what type of sensor, that Hall effect sensor that we are using, what was the cost involved in that one? Okay, what is its accuracy, what is its noise suppression capability, all these factors will also be accounted for. Now coming to the open circuit voltage method. The second well known method is open circuit voltage method. So in this principle what happens, the battery voltage principle is that the battery voltage when no current flows, rest state correlates with the state of charge. So under the offline condition, when we are not draining the battery or not we are charging the battery, so if we are able to measure the terminal voltages, okay, because under steady state condition it is expected that terminal voltage will be somewhat steady, fixed, it won't vary. So it is measured, and we are already having some lookup table. So with respect to the terminal voltage, what is the expected state of charge? Okay, that curve, from there we can compute the or find out the value of the state of charge. So use pre-calibrated open circuit voltage and state of charge curve for the estimation. So it is best suitable for long idle period, when the vehicle is not moving, or suppose a battery bank is there, it is not in use continuously. Okay, such as grid storage, stationary system, for those long idle periods can be there. So there it is easier to estimate the state of charge. Where it is not suitable for dynamic systems like electric vehicles continuously moving. Okay, so that discharging will be there, then regenerative braking, so it will charge up to a certain extent, then discharge. So that type of dynamic system, it is not worth to go for this type of method. So due to constant current flow, okay, so requires long relaxation time, 2 to 6 hours. Okay, so example can be like lithium ion open circuit voltage, state of charge curve. So lithium ion, some batteries, so different batteries will have different relationship curves. Okay, it is non-linear, flat at the middle, strip near 0% and at 100%. So if there is a curve, that will be better to show you. It is not shown here. So now come to the that explanation, further explanation, that open circuit voltage based state of charge estimation. So how it is done? Simple polynomial based curve fitting we are applying. Okay, as already mentioned, the curve will be somewhat non-linear. Okay, so in that it is not like x-axis and y-axis, it is linear, it is non-linear. So in that non-linearity, what happens? Flat at the mid SoC, it is somewhat constant during mid part, and near 0% it is slightly rising, and after that it will again be somewhat rising, like that. So with a function of voltage, open circuit voltage, the state of charge is directly proportional. So you can say state of charge measured open circuit voltage, and function of that function is nothing but it is representing a polynomial which will be able to depict or do a curve fitting, polynomial fitting. So practical use, a lookup table or a polynomial fitting is used, often used to map the open circuit voltage with the state of charge. So simply any generalized polynomial can be have a constant term, okay, intercept value, that is used for offsetting some reference points, then a1 into VOC to the power 1, then a2 into VOC to the power 2, and up to nth order it can be made. So this requires battery to be at rest, no load, for several hours for an accurate reading. Okay, so for several duration it should be under this condition. Equivalent circuit models. So models battery as voltage source plus resistors plus capacitors. So equivalent circuit models means we are trying to estimate the state of charge of the battery by using proper equivalent models. In equivalent models, we are trying to use some components, R, L, C components. Mostly it is R and C only, because in battery inductive part is not there. Mostly it is capacitive and resistor. And here you can see these are the different possible models. Okay, number of, like it's a open circuit voltage, then resistor, C1, R1. So some different types of diagrams or circuits can be used to represent the battery model. Okay, this is the simple battery that we can consider, and this is the equivalent circuit model. One open circuit terminal voltage will be there, then other components can be selected, and what should be the magnitudes that need to be decided. Once these things are fixed, then you have to apply some Kalman filter techniques. Kalman filter is nothing but state estimator which uses a model and real-time measurements. Whatever measurements are possible for any system, that will be used to estimate the non-measurable parameters like the state of charge, the adapt to system noise, sensor noise, and non-linearity. So what are the pros over here? More accurate under load condition, and correct drift of coulombs counting. Okay, correct the drift of the coulombs counting. Some of the disadvantages that was there in the coulomb counting, that drift or that initial guess, that is being overcome in this method. So enables real-time SoC tracking. So what is the disadvantages? This is a complex computational technique. In fact, this extended Kalman filter, it involves 5 equations. I have not shown the equation because it is something related to master's syllabus. Okay, MTech, those who are going to do MTech in control system, mostly they will be going for this Kalman filter. To avoid any complications, I have skipped that slide. So here implementation is complex, needs accurate model. So out of these different varieties of the models, which one is accurately resembling the functionalities of the battery is very difficult to say. So sometimes it is expected, the simpler it is, the better it will be. Whereas if we are considering more number of components, then that will be somewhat better. But it is like computationally more inefficient if we are considering more number of components. So somewhat trade-off need to be done because between the number of components and accuracy involved. Okay, so demands higher processing power, so definitely processing will be also increased. So these are the disadvantages of Kalman filter based or you can say model based state estimation. So here some diagrams or some equations involving that Kalman filter is shown here. So it is having state prediction equation. Okay, at any particular condition, what is the state that can be determined by the previous state and rate of change of the time with respect to current, and this Wk represents the process noise, system noise, whatever is there. The nominal capacity of the battery is C nominal. Okay, similarly voltage measurement equation means we are able to measure the terminal voltage. So that measured value will be provided as input to this model or this Kalman filter. Now these are the prediction equations and these are the measurement equation and correction equation. So these are the 5 equations involved in any Kalman filter. It comprises of 5 equations. Okay, so this is what, and I am not explaining these things in detail because just now I mentioned this is a master's level and it will be deviating from this topic. So I will skip this part. Those who are interested, they can definitely explore more about the Kalman filtering. Now coming to the hybrid method. So in any battery applications, just now we have seen 3 different types of methods are there. So why not select any 2 of them depending upon the requirement? So combining Coulomb's counting with open circuit voltage or apply EKF or even neural network based, ANN based with the growing demand for AI, lot of AI based techniques are also available. So machine learning based estimation, trained for historical battery data, that can be also evaluated, can model aging, temperature impact. Okay, so different unaccounted parameters like temperature impact, aging, these things also can be accounted for. Then state of function and state of health integration can also be measured. Okay, now, so this was all about the state of charge estimation. Now, to give a brief summary between different techniques. So, Coulomb's counting method, it is somewhat accuracy is medium. It is possible for real-time application. Its complexity involved is low because just we need to monitor the charging and discharging current using Hall effect sensors. So what are the drawbacks? It accumulates error. So that initial guess, if not correct, definitely that error will persist and it will definitely may make the final outcome wrong if that initial guess is not done correctly. Then open circuit voltage method. So here accuracy is high. Real time it is not suitable because already mentioned the battery need to be idle. It has to be not in use for at least 4 to 6 hours. Then complexity is medium because only that polynomial equation we need to derive. Then needs idle time. Then Kalman filtering. So it is accuracy is higher, real time also possible, but complexity is more and requires model means that equivalent circuit model you need to know, you need to have that state estimator means state space model you have to develop. Okay, then hybrid model means combination of any 3 of these, so very high accuracy will be higher. So then real time application will be probably possible, complexity will be higher and integration will be also more complicated. Machine learning based, so here accuracy will be more, real time also possible, complexity will be higher because training of data will be there. That drawbacks is needs large data set. So as mentioned, so all these different techniques are available for evaluating the estimation process of state of charge. Now coming to the second part of this lecture, that is state of health. It is also one of the important component for the battery to determine whether the battery is still suitable for electric vehicle application, means above 80% is it possible for the battery to retain its capacity or not. If not, then definitely we will go for the second use of life. So that also we will see. So what is state of health? In basic language, it is a quantitative measure that indicates how much a battery has degraded over time compared to its original condition. So a newly manufactured battery will be definitely capable to store more charge as compared to a degraded or old one, 2, 3, 4 years old battery. Like in our mobile phones, in laptops, we might have seen as the time is goes by, suppose 1 year, 1.5 years, the storage will show 100%. But when we are using that one, within half an hour, 1 hour, or 1.5 hours, it will drain. Okay, completely zero. Whereas a newly purchased laptop, the battery retention is almost 3 hours plus, 4 hours, like that, if it is used optimal way. So like that. So definitely it will, in numbers it will show 100%, but in the background it is not able to store the 100%. It is draining at a faster pace. So present capacity or performance divided by initial capacity or performance. So this is also expressed in percentage. That's why we are multiplying 100. So SoC close to 100 means it is a healthy battery, newly developed. Then state of charge less than 80%, that reduces the efficiency, often considered threshold for end of life in electric vehicles. So just now I mentioned, if the efficiency is less than 80%, then that reduces the efficiency. Okay, if the state of health is less than 80%, it will reduce the efficiency. Now coming to why it is important. So it is useful to determine the battery reliability and remaining useful life. So if it is close to 100%, means it's a new battery, it will run at least 4-5 years. But if it is less than 80%, definitely hardly 6 months or 1 year it will last. Then essential for predictive maintenance. So if some fault is there, some error is there, so if proper health is not maintained, so definitely we can call for some predictive maintenance. Instead of waiting for the battery to fail, we can do some repairing work, some upgradation work. Then enables safe operation. So by avoiding thermal and voltage stress, it will be safer to operate. Then required for warranty validation, fleet management, and grid backing planning. So these are all higher end applications where multiple vehicles are being used. So which battery will be put in which vehicle, so fleet management is there. Then grid level backup planning, so how much the battery bank will be able to supply for the duration. So what is the capacity, hours of backup required. Okay, what is the percentage of critical load involved. Okay, warranty validation, how much is the warranty period. So all these things comes under the health, state of health. Now what are the key indicators of state of health? So two factors are involved in that. So first one is storage capacity and internal resistance. Okay, so storage capacity, first capacity fade or degradation. As the time passes, the holding charge, the loss of total charge holding capability, like already mentioned, how much charge it is able to store, so that will degrade with time. So loss, that degradation, that loss of total charge holding capability or reduction in the total charge a battery can store due to, what are the causes behind this degradation? SEI, that is solid electrolyte interface, or growth. That means some layer will be formed between solid electrolyte, it can be cathode, anode, so, and liquid electrolyte is there, electrode and electrolyte. Between that layer, like in the water tanks where cement or plastic is used, and definitely because of the flow of liquid, definitely some green algae are formed. So that interfacing, that layer formation is called the SEI, solid electrolyte interface growth. So active material loss, or it can be that anions, cations being degraded in the electrolytes, electrolyte decomposition, repeated cycling, okay, continuous charging, discharging, charging, discharging, so that will damage the battery. So it is expressed in terms of simple, that is what is the actual storage capability divided by rated or the newly built battery, what is the storage capability. So this is the state of capacity. Okay, state of health, subscript capacity we are considering. Similarly, come to the second parameter, that is internal resistance increase. So for a older batteries or aged battery, the internal resistance will be more, like for humans or even animals. So as the person is aging, the bones get weakened, okay, so they will be loose, okay, like that we can consider. So it increases the internal resistance, results in voltage sag and heat generation, okay. So internal resistance will be more as the battery is getting older. So reflects power delivery ability of the battery will be reducing, okay. So it is expressed as SoH resistance, which is equal to R initial. Newly purchased battery will have a lower internal resistance. So this numerator is lower compared to the increased internal resistance because of the aged battery. Okay, it will be more multiplied by 100. So all these things are expressed in terms of fractions. Okay, so as R increases, more heat, faster aging, leading to performance and efficiency drop. Like young persons, those who are running, similarly a old person running, definitely difference in the speed will be there, because the old person's bones are weaker. They will not be able to sustain that much fast speed. So like that, the older battery will have higher resistance, so it will not be able to store more energy, and definitely heat losses will be also increased. Now other things are power fed. So these are also directly related to the state of health. Power fed means directly related to internal resistance and voltage response. So under load, okay, what is the internal resistance, what is the voltage response? So impact peak current and acceleration in the electric vehicle. So how much required acceleration is there, it won't be able to support because of the weakness, because of the degraded capability of the battery. Similarly, self-discharge rate. So a degraded battery loses the charge faster over time. So what is self-discharge rate? I will explain. Even if we are not using the battery for a certain duration, what will happen? So suppose for 1 month we are not using, suppose we are making it 100% charge, we are not using the battery. So after 1 month, definitely 3-4% it will be lost. So that automatically loss of the charge, even if the battery is not in use, when a prolonged duration is given, so that is called state of self-discharge rate, okay, and it is measured per month, okay. So a degraded battery loses charge faster over time at rest, okay, even if it is not in use, still it will lose the charge. It indicates chemical instability or electrolyte breakdown. This is the main reason because of which it will be taking place. Now coming to the other two things, that is voltage and temperature deviation. Definitely if the state of health is not good, so cells showing faster voltage drops or higher temperature under, so all these are interconnected. It's not like they are independent. Mainly it is confined with the resistance increase and capability reduction, fading in the capability reduction, and all are indirectly related to that. So charge cycle count, depth of discharge, okay, number of charge discharge also will be reduced. Shallow cycles, like we cannot make the battery wait to get discharge up to 0%. When it is up to 20-25, then suddenly the remaining battery will be gone within minutes. So that retention is very low, less, okay. So depth of discharge will be also getting affected. So these are some of the indicators of state of health degradation. So here it will be clearly analyzed. For a new battery, 100% state of charge is there. For a older battery, aged battery, suppose state of health is degraded to 80%. So this is the degraded part, but in the output it will show, okay, 100% state of charge is there, but it is still, you can see it is not getting the remaining 20% charging. It will show 100%, but actually it is at 80% charge. Similarly, and this is 60% state of charge for 80% state of health. Okay, if this will be considered as 100, so this will be considered as suppose 60%. So here you can see state of health means some portion will never get charged. Okay, and once this is around 20%, means only 80% we are able to charge, that battery is not suitable for electric vehicle application. We have to replace it for end of life or second life usage. Okay, so that is what it is depicting. And here you can see the 100% state of health is this one. Okay, so if state of health is 66% and the battery is charging up to this much, and this itself will become the 100% of state of charge, not the final one, because this part will never get charged. Okay, so this is what the same things are represented here. State of charge is this full part, depth of discharge is what percentage is reduced below. Round trip efficiency means one full charging cycle, one full discharging cycle. So what is the total efficiency? It will definitely, for a new battery, it will remain around 90-95%. Okay, self discharge rate means even if you are not using the battery, it will be discharging automatically, but the duration it will take is longer, almost 1 month at least, to have a 1 or 2% drop in the state of charge. So now coming to the state of health estimation, we have just seen what is state of health. So here now we will see state of health estimation. So here also Coulomb counting method is there. It is somewhat similar to the state of charge estimation. So here state of health is nothing but measured capacity by rated capacity, or Q discharge by Q nominal. Okay, and C is just nothing but the total current integration of the current, total area covered by the current, that is showing the capacity. Okay, then incremental capacity analysis. Incremental means rate of change of charge with respect to voltage from voltage capacity curve. So this is another curve where voltage can be measured and what is the capacity can be measured. So change in the peak structure indicate lithium plating, ACI thickening. So these are the factors that will affect the state of health. So incremental capacity analysis. So this will also be used to know the state of health. There are some instruments also, that is electrochemical impedance spectroscopy, EIS. It is a very sophisticated electrochemical techniques that measures the AC impedance across the frequencies. Okay, multiple frequencies will be provided and it will measure the internal resistance. Okay, identify the internal degradation by observing charge transfer resistance, diffusion resistance. It will plot some curve, mostly control related Nyquist and Bode plots, and it will give you the outcome, how much is the loss is there in terms of degradation. Then of course Kalman filter based estimation. Kalman filter can be used in any application because it's a generalized state estimator. Okay, optimal state estimator. So here definitely first you need to create a battery model. You have to add the process noise and measurement noise in the output. X is the state vector. So what are the components that we can have? The sensor data that we can provide is voltage, current, temperature, state of charge behavior can be estimated like already discussed. Okay, then of course machine learning technique is there. So it will be used to train different models like voltage, dV by dt curves, okay, current profiles, temperature. So different algorithms we can apply to estimate the state of health. Then direct some lab based measurements are also possible. Full charge discharge test to determine the actual capability. So make the battery fully charged, note down the duration and use the battery so that discharging takes place, note down the duration, how quickly it is getting discharged. Through that analysis also, if a proper record is maintained, definitely it will be able to estimate the state of health of the battery. So accurate but time consuming. So multiple charging discharging cycles will be observed. That's why it is more time consuming, impractical for real time use. Okay, so mostly in state of health we will be using this EIS method, Kalman filter is possible, AI based method is possible, and of course Coulomb counting and incremental capacity analysis are also feasible for state estimation. Now here this is the different tests that are possible: experimental analysis, capacity test, ohmic resistance, EIS analysis, okay, different ultrasonic, fiber. So lot of possible physical test equipment based analysis is there. Some observations can be obtained. What are the direct observation? What is the quantity of Coulomb, internal resistance, DC, internal resistance, AC, then aging mechanism, okay, indirectly internal flows, any strain, temperature, any part is getting more heated. Okay, so all things can be computed. So compare and measure. So rated value and state of health will be noted down like this. So what is ICA that we have just now seen? Incremental capacity analysis. DVA means differential voltage analysis. So these are also some form of algorithms only to estimate the state of health. So once the state of health is known, finally we can decide whether it will be went for second life use or it will be sent for recycling once it is less than 80% of state of health. Similarly, for AI, ML or some algorithm based estimation, so some data set will be there, training will be involved, okay, charging data, discharging data, some curves will be provided as input, feature data set extraction feature extraction will be there, then training the features, particles one optimization. So different techniques are there, so we will not go into that much detail of this AI, ML based technique. So training set is there, feature set is there. Okay, so at the end we will be able to estimate what is the state of health. Now coming to the comparison of all these methods. So Coulomb's counting method, what is there? Real time possibility is there, of course, or it is not possible for Coulomb counting. Impedance also, spectroscopy, instrument continuously we cannot use. Whereas the other three methods, ICA, then Kalman filter and machine learning, we can go for that one. And these are the things that we need to note down, like hardware needed. So Coulomb's counting sensors are required, frequency response is required for that EIS technique. Then ICA we required voltage, capacity and logs. Basic sensor models are required. Historical data sets are required for machine learning approaches. Okay. Now, what are the different influencing factors that are that can make the state of health estimation wrong? Okay, so or the things that need to be accounted for are like design parameters, like cell design, choice of anode and cathode electrolytes, then pack design, mechanical stress, cooling systems, all these things. Then production. In production, what are the factors that we need to consider, like production line humidity, electrolyte filling methods, formation methods, then aging methods, okay, applications where we are been using these batteries, high temperature, low temperature, current load, low voltage, high voltage. So what are the reactions that because of these things, what is the changes that are happening, like electro or particle cracking, SEI film formation and thickening, transition metal dissolution. So these things will be taking place. Cathode, that layer electrolyte interface is there. SEI and CEI are quite similar. And then lithium plating, graphite exfoliation, then binder decomposition, structure disordering. So these are the things that will be taking place, because of which the ultimate that the battery will be degraded, loss of lithium ion inventory, loss of anode cathode activity material, loss of electrolyte capability, resistance increment is gone, then effect capacity fed, power fed, these things are happening. So this also resembles the similar things like time, aging factors, high temperature, high state of charge, low current, low state of charge, degradation mechanisms like this growth, all these things we have discussed now. Okay, so what will be the ultimate outcome? Conductivity will be lost, loss of active positive electrode material, loss of active negative material, loss of lithium inventory. So these things are taking place. So what are the different factors? What are the degradation mechanism, how the losses will taking place, and how it will impact. Okay, that is what we are analyzing over here. Now, towards the end, we can discuss that battery management integration and real-time monitoring. So, battery management system, what we are expecting, it should be able to continuously monitor the voltage profile during discharge, charge throughout per cycle, charge throughput per cycle, temperature under the load, resistance spikes, cycle life counter, all these things it should be able to estimate. Then real-time estimation challenges, what are the challenges that we can be facing because of Aging is non-linear, temperature dependent. So accuracy will be not if the temperature is more. Then need for partial cycle estimation. Okay, calibration needed for to avoid the drift. So definitely some basic calibration or some experienced personnel are required to make the initial guess. Okay, so these things need to be accounted for while making the battery management integration of the state of health and state of charge, okay, for the real-time monitoring purposes. So what are the things, real-time inputs that are required? Voltage drop under load, then current peaks, temperature rise, okay, coulomb throughput, then charge discharge duration. So integrated approach like modern BMS combines data-driven, machine learning based, model-based Kalman filter techniques to estimate the state of health in live environments. Okay, often embedded with the microcontroller. So multiple. It is better if when we are in doubt, definitely if we'll combine one or more techniques, one way or the other way, if accuracy will be enhanced. And of course, computational burden will increase, but if accuracy is of utmost importance, we can combine one or two methods together. So, what are the different things involved? Same things it also represents, like PTT pulse testing technique, partial charge PC based methods, okay, ultrasonic inspection, AE sensing is there, acoustic, that sound based sensing. So these are just methods to estimate the state of health where it is applied. Okay, cell battery level, module pack level, okay, say cell battery level, module pack. So these are the application. What are the modes? Most of them are offline. Online is only PC based method is online. Here it is online, and these last three are online. Otherwise, most of the others all are offline. Then what it indicates? So internal resistance, impedance, charging data. Okay, all these things can be estimated. Now a basic comparison. This is the last slide. So what is the summary of that study of the state of health? So capacity, resistors, cycle count, temperature, voltage response, all these things impact the state of health in terms of direct degradation. Resistance will affect the power fed and heating. Cycle count will show the aging indicator. Accelerated degradation will be appearing. Then cell imbalancing or some form of deviations will be observed. Okay, how it can be measured already we have discussed. Then Coulomb counting method is for capacity full. Then resistance can be measured with pulse test, impedance methods. Usage can be usage logging can be used for cycle count. Okay, then thermal sensors, BMS logs. Then load testing, dV by dt testing behavior can be used for voltage response. So with this we have learnt about the state of charge and state of health estimation. So of course these are somewhat technical, some mathematical equations were involved, but once these two important parameters are estimated properly, then only we will be able to make the battery management system work in a better way, because most of the other parameters can be measured using some or other instrument, whereas these two, health and state of charge, need to be estimated. So today we learned those two in somewhat detail, and definitely next we will continue from here. So thank you.